There's a saying in cosmology that has always puzzled every one of us: the two darknesses, one black, and three origins. The two darknesses refer to dark matter and dark energy, the one black is black holes, and the three origins are the origins of the universe, consciousness, and life. But have you ever wondered why the two darknesses come first? They make up 95% of the universe's total mass, yet we've never seen them. How did they even come into existence? And how do they secretly control the workings of the universe behind the scenes? Online, explanations about dark matter and dark energy are everywhere, but when it comes to the core question, no one can give a clear answer. Today, we'll start with this most elusive problem, and take you through some perspectives you've never heard before. This content is deep, recommended for those with some basic cosmology knowledge. Otherwise, your brain might start itching by the end. We reused to dividing the universe into two parts, the visible and the invisible, but the existence of dark matter and dark energy completely challenges this simple classification. They don't just stay hidden, they control the entire universe. By being absent, the physical laws we know seem powerless in their presence. They like invisible rulers hiding in plain sight, silently manipulating cosmic expansion, the formation of galaxies, and possibly even the ultimate fate of the universe. So why can't we see them? The problem lies in the fact that our senses and tools are designed for the perceivable world. We rely on light particles colliding and sound waves vibrating to understand the universe. But these methods have no overlap with dark matter or dark energy. Their existence doesn't create vibrations in physical space, but operates at a deeper level, subtly influencing the fabric of the universe by altering our understanding of space, time, and mass. But have you ever wondered what the universe would look like without these unseen forces? Without dark matter's gravitational pull, would galaxies drift apart? Without dark energy's push, would cosmic expansion stop, or even reverse? These questions might sound abstract, but they strike at the heart of our fundamental doubts about how the universe evolves. Yet, to this day, we have almost no clue what dark matter and dark energy actually are, or how they work. What do they really look like? Why are they so elusive? The answers might not just determine the fate of the universe, but also how we perceive reality itself. The next phase of exploration could peel back a corner of these mysteries, revealing shocking truths behind them. In quantum physics, there's a particularly baffling phenomenon called quantum tunneling. Simply put, it means microscopic particles can pass through barriers that should be impossible to cross, like energy walls. Sounds unbelievable, right? In classical physics, we assume a particle needs enough energy to overcome an obstacle. But in the quantum world, particles seem to teleport, appearing on the other side instantly, defying conventional rules. Quantum tunneling might seem like a challenge to classical physics, but it could also help us solve some of cosmology's biggest puzzles, especially dark matter and dark energy. These two mysteries have stumped scientists for decades. Dark matter and dark energy make up 95% of the universe's mass, yet we've never directly observed them. Our current technology can't even detect their traces. So, what's the connection between quantum tunneling and these invisible forces? First, dark matter and dark energy have never been directly observed. Scientists can only infer their existence by studying their effects on large-scale cosmic structures and the speed of expansion. But how do they form? How do they interact with ordinary matter? These questions remain unanswered. However, if we consider quantum tunneling, maybe they influencing the universe in ways we can't perceive, through some kind of quantum leap. Imagine this: dark matter and dark energy aren't fixed substances, but instead seep into our universe from another dimension, or parallel reality through quantum tunneling. Maybe, at the moment of the Big Bang, some quantum process allowed them to cross over from the microscopic scale into our cosmos. Quantum tunneling could not only help us understand how these invisible entities formed, but also reveal their subtle relationship with ordinary matter and energy. For instance, if dark matter and dark energy really did tunnel into our universe from another reality, they might affect the rate of cosmic expansion, or even alter gravity and matter distribution. This wouldn't be an impenetrable black box anymore, but a process explainable through quantum phenomena. In other words, everything might trace back to a quantum leap, a shift in the laws of physics, under extreme conditions, creating microscopic, crossings we can't observe directly. The mysterious nature of quantum tunneling might reveal a more dynamic, non-linear model of the universe. The cosmos isn't static, its composition and evolution could be constantly influenced by quantum effects. As fundamental parts of the universe, dark matter and dark energy, their emergence, changes, and even disappearance, might be deeply tied to quantum tunneling. And quantum tunneling's influence doesn't stop there. It could also play a key role in other cosmic phenomena, like the birth and death of black holes, the acceleration of universal expansion, and the evolution of galaxies. These seemingly classical events might hide quantum effects beneath the surface. Quantum tunneling could be the bridge linking macroscopic phenomena with microscopic laws, showing us a far more complex and unpredictable universe. These tiny quantum effects might be the fundamental forces driving the cosmos. We might be living in a quantum-powered universe, with dark matter and dark energy as its most mysterious and crucial components. But how do they interact with the familiar world of matter? That's a question that might require major scientific breakthroughs to answer. Take the Higgs boson, for example, dubbed the God particle. Its discovery shook the world of physics. In 2012, scientists at CERN's Large Hadron Collider finally detected it. This wasn't just a monumental breakthrough in physics, it deepened our understanding of how the universe is structured and how it functions. But have you ever wondered why the Higgs boson is so important when discussing dark matter and dark energy? First, let's revisit the Higgs boson's basic significance. It's a particle closely tied to mass. According to the Higgs mechanism, fundamental particles in the universe gain mass by interacting with the Higgs field. This mechanism provides the foundation for the entire cosmic structure. In other words, the Higgs boson is the source of mass in the universe. Without it, particles would be massless, and galaxies, stars, and even life on Earth couldn't exist. So, the Higgs boson isn't just the guardian of cosmic mass, its existence determines whether the universe can evolve into what we know today. Without it, reality as we understand it wouldn't be possible. But how does the Higgs boson connect to dark matter and dark energy? Part of what makes dark matter and dark energy so mysterious is their extremely weak interaction with ordinary matter. Observations of galaxy rotations and cosmic expansion suggest they play a massive role in the universe, yet we can't directly detect them. Even their basic properties remain undefined. The discovery of the Higgs boson might offer some answers. One hypothesis suggests dark matter could consist of special particles that interact with the Higgs field, gaining immense mass but not interacting with light, making them invisible to us. In other words, dark matter particles might be a type of Higgs particle, acquiring mass through the Higgs field but remaining unaffected by electromagnetic forces, rendering them undetectable by traditional means. Even more exciting, the Higgs boson might provide new insights into dark energy. Dark energy drives the universe's accelerating expansion, but its nature lacks a clear physical model. If we apply the concept of the Higgs field, we might find a fresh explanation for dark energy's origin and properties. Perhaps certain features of the Higgs field play a key role in pushing cosmic expansion forward. From this perspective, the Higgs boson isn't just the source of mass, it might also be the bridge connecting ordinary matter, and dark energy. We've long treated dark matter and dark energy as cosmic unknowns, but through the Higgs boson, we might uncover their roles and relationships in the universe. So, how does the Higgs boson's discovery change our understanding of the cosmos? Imagine this: as a fundamental particle, the Higgs boson lets us glimpse the universe's most elusive aspects. The mysteries of dark matter and dark energy are no longer just vague concepts, but are slowly coming into focus through the Higgs mechanism and quantum physics. They might be products of the Higgs field and quantum effects, hinting at deeper interactions between matter and energy that we've yet to fully grasp. Thus, the discovery of the Higgs boson isn't just a revelation about cosmic structure, it might mark a crucial step toward solving the universe's greatest enigmas, the true nature of dark matter and dark energy. Of course, we might still never fully solve these puzzles, as the universe is far more complex than we imagine. But this discovery undeniably reveals potential links between ordinary matter, and dark energy, and that's the beauty of scientific exploration. Every answer leads to more questions.